Okay, problem number 1. It says 4 problems 1 through 3 condense the expression into a single logarithmic expression. So just as a quick recap of your properties of logs, we had 3 of them that we focused on. The first one said if you had something like log x squared, that you could take the exponent and move that out front. Okay, and make it 2 log of x, okay? And so this is actually reversible, so it's an arrow that goes in both directions, which means if I have a 2 or any number in front of a log, that I can move that back inside, right? I can make it x squared if it's out front, or I could take the squared and move it up front, okay? The second property said if you have a log of x plus log of y, which means addition in between 2 logs of the same base, then you can put those numbers, x and y, into the same log as long as you multiply them together. So again, this is reversible as well, which means if you have 2 factors inside of a log, you can reverse that and give each of them their own log with a plus sign in between them. And then the same thing is true of subtraction. So I could say log of x minus log of y becomes log of x divided by y, and again, reversible, which means I can go in the other direction. So for these problems, you're just going to go kind of step by step through these and combine them, which means we're going to be pretty much traveling in this direction for the plus and the minus ones, right? We're going to be traveling to the right, okay? So with this problem, what I'm going to look at each of the terms, I'm going to say if there happens to be any number sitting out front like this 2, which we call these coefficients, if there's any coefficients in front of the log, we're going to bring those back inside. So I'm going to do that for each of these, right? So we have to be careful. So I'm going to just bring in the 2 and bring in the 4, and it's going to look like log base 4, okay, of 3x squared, okay? And then when I bring in the 2, it's going to say squared, okay? I'm going to make my pencil tool a little smaller. It's a little bit too thick, okay? And I'm going to do the same thing with the next one. So I'm going to bring this 4 inside. It's going to say log 4, okay, of y to the 4th, okay? And then the log z doesn't have anything, so I'm just going to leave that as log 4z, okay? So I'm going to simplify now. This really, when I square 3x squared, what I'm saying is 3x squared times 3x squared, which is 9x to the 4th power. So I'm going to write that out. Log base 4 of 9x to the 4th plus log base 4 of y to the 4th, okay, minus, oh, I missed it up, minus log base 4 of z, okay? So let's try that again. Log 4 of z. Okay, so now I'm just going to go left to right. So I've kind of like done all of the coefficients. That's finished. So now I'm going to go left to right, and I'm going to use these other 2 properties. Anytime I see addition between 2 logs, I'm going to multiply. So let's do that. That's happening right here. So I can multiply together the 9x to the 4th and the y to the 4th and combine them into a log. So log base 4 of 9x to the 4th, y to the 4th. We can't combine those really. So this is really the best that I can do. And then I still have this log z. Okay. And so now I'm going to move, that's all of my addition. So now I'm going to move on to the subtraction, and it says if there's subtraction between logs, divide. So I'm going to say this is now log base 4 of 9x to the 4th, y to the 4th over z. Okay. I've now condensed this expression into a single log, nothing outside of it. This right here is my answer. Okay. So I'm going to go through the other ones a little bit more quickly. We'll have some fine details to explain. Okay, I'm going to get rid of my properties here because we know them now. Okay, so your second problem says 1/3 log base 2 of 27x to the 12th minus log base 2 of 3. So again, first thing, I'm seeing a coefficient up front, so I'm going to move that inside. So it's going to say the log base 2 of 27x to the 12th, okay, to the 1/3 minus log base 2 of 3. Okay, so again, we have to figure out what does this 1/3 mean? Well, we're going to bring it inside first, okay, and deal with them separately. So the property of the property of exponents says give the 1/3 to both the 27 and to the x. When I'm giving it to the x, because there's already a 12 there, I'm going to multiply those together. So I'm going to do 12 times 1/3. So this simplify step looks like log base 2 of 27 to the 1/3. And then when I combine it with the x, it's going to say x to the 4th, because 12 times 1/3 is 1/4. Okay? So now, okay, we're going to do 27 to the 1/3. 27 to the 1/3 is just 3, right? It's the cube root of 27. So I'm going to say the log base 2 of 3x to the 4th minus the log base 2 of 3. So now I have subtraction in between two logs, which means divide them. So log base 2 of 3x to the 4th over 3. And now I can do a little bit of canceling. So we're simplifying if we can. 3 divided by 3 does cancel. My final answer is going to be the log base 2 of just x to the 4th. And that would be 1 log condensed and simplified. Okay. So last problem, probably the trickiest of all them, again, because of the fractions. We have to remember how to handle fraction exponents. Okay. So I'm going to bring the 3/2 in. It's going to say the log base, the log with no base, which we know is 10, the log of 4 to the 3/2 minus the log of x to the 8th to the 1/4. Okay, so the 3/2, remember, without a calculator, this is the no calculator section, so you have to be able to do this without a calculator. Okay, this means the bottom of the fraction means take the square root, right? This is the root, so I'm going to take the square root of 4, which is 2. 2 to the 3rd power is 8. So this really just means the log of 8. Okay, so again, you have to be able to evaluate fraction exponents without a calculator. Okay, and again, when I bring the 1/4 into the to the exponent, to the x, it's already got an exponent, so I'm going to multiply those together. 8 times 1/4 is 2, so this is really just the log of x squared. Subtraction in between my logs means divide, so I'm going to turn this into now the log of 8 over x squared, and that is now in simplest form, 1 log. Okay, so again, make sure you know your properties of logs, and make sure that you know how to handle exponents using exponent rules. Make sure you know how to handle fraction exponents, even complex ones like 3 over 2, right? So you have to be able to do all of those skills without a calculator. Okay, problem number 4 and problem number 5 is basically saying solve, okay? And I'm putting big bold letters here, check for extraneous solutions. That means anything that doesn't work inside of a log, we have to throw away. Okay, so our first problem, I see a logs on the left and logs on the right, and we have a 1-to-1 property that says if you can get it down to be 1 log on the left, 1 log on the right, you can throw away the logs. So we're going to do that. Plus sign in between two logs means multiply them together, so I'm going to do that first. We're going to say the log base 3, x times x minus 1 is x squared minus x is equal to the log base 3 of 6. Okay, so I have my ideal situation now. I have logs on both sides, nothing else floating around outside, so it means I can throw away, okay, the logs entirely. They are not relevant to our problem. Solve this by getting x equal to 0, so x squared minus x minus 6 equals 0, and then I'm going to just factor and solve. So this becomes x minus 3, x plus 2, okay. So I get two solutions, and again, we got to be careful with our solutions. Our solutions here are 3 and -2, okay? If I check 3, I'm fine. And again, if you're unsure about how to check for extraneous solutions, here's the idea. I cannot log 0, and I cannot log negative numbers, which means if I plug in the 3, what I'm checking is when I plug in the 3, does the inside of the log simplify to 0 or a negative? And if it does, I have to throw that away. In this case, when I plug in the 3, it says 3 minus 1, which is 2. 2's positive, that's good. When I plug in a 3 here, it's just log base 3 of 3. That's good, I can do that. Okay. -2, though, presents a problem in both of them because this says log base 3 of -3, and this says log base 3 of -2. I can't log negatives, which means I'm going to say goodbye. I cannot use that problem. Okay. So let's try problem number 5. Similar, I'm seeing 2 logs on the left, so let's fix that. Okay, so I'm going to say subtraction in between logs means divide those logs, so I'm going to say divide what's inside of those logs. The log base 2 of x plus 6 over x minus 3, okay, equals 5. Be careful here. If you take a look at problem number 4, there was a log on the right, and that's what let me just drop the logs off the problem. It has to be logs on both sides. Problem number 5 does not have a log on the right, so I need to go back to the definition of what logs are and convert it into exponential form, okay, which is, in this case, I'm going to say base exponent output, so I'm going to say that x plus 6, okay, x plus 6 over x minus 3 is equal to 2 to the 5th power, okay? So 2 to the 5th power is 32, so x plus 6 actually equals 32, not just 5. Okay, so when I cross multiply, okay, it's going to be like this is over 1, so it's x plus 6 times 1, well, that's just x plus 6, okay? And 32 times x is 32x, okay? 32 times 3 is 96. Okay, so it's minus 96. So I just have to solve this linear equation now. This is pretty straightforward. I'm going to subtract the x over. It's going to be 31x. I'm going to add the 96 over it becomes 102. And when you divide on both sides, to the best of my knowledge, this does not simplify at all. We're just going to leave it as 102 over 31. Okay, so this is our answer. I'm going to do a quick check. 102 over 31 is a number bigger than 3, so my only issue with getting an extraneous solution would have been here. But if I have something bigger than 3, that will stay positive, so this is actually a good answer. Okay, so solving logs, we have two possibilities, either the log one-to-one property, which means logs on both sides, or just turning it into an exponential once you have your log isolated. Okay, problem number 6 and 7 say, if we have some parent function, in this case they're giving us 3 to the x, they want to know if I have some point on 3 to the x, and then I use this new equation, this new function here, negative 2, this has got a bunch of other stuff going on, where does a specific point from 3 to the x end up after all the transformations? So in this problem they're saying f of 2, right? So let's talk about what that means. F of 2 means go to f, plug in a 2, tell me what happens. So if I plug in a 2 here, it becomes 3 squared, which is 9. And so what that means is that on the parent function, on f, when I plug in a 2, I get back a 9, which means that's a point that exists on the parent function. So what they're basically saying is, after I transform 3 to the x into problem number 6 here, if you notice this is also 3 to the x, but with all of the other transformations, the a, b, and a, b, c, d values, where does 2 comma 9 go, right? So if you think back to when we talked about transformations, I gave you this nice chart here, which basically said, if I transform using b and c, that's going to change the x coordinate, and if I use a and d, that will transform the y coordinate, and we transform them using multiplication addition, right? So really this is what we're doing on the point 2 comma 9. So we need to look at our function g of x and say, looks like negative 1 is the a value, I have another negative 1 for the c value, and it looks like I have a negative 4 for the d value, no b at all, so I'm not going to use those, right? So let's do our transformations on 2 comma 9. So I'm going to start off with 2 comma 9, okay? And I'm going to go across this list. I'm going to say b transformations. No b value, skip it, okay? C transformation. A C transformation says add c to the x value, which means 2 comma 9. Be careful again, c is actually negative 1. It's not 1, okay? So I'm going to say add negative 1, and that would become 1, okay? So let's fix that. Okay, so 1 comma, I gotta fix my pen now, okay? So it would become 1 comma 9, okay? That would be adding negative 1 to the x value. And now I'm gonna go to the next one. It says multiply the a value by y. Well, my y in my most recent kind of iteration of this point is a 9. Multiply that by negative 1, so this is my a transformation, will become 1 negative 9, right? And then I'm gonna do a d transformation, which says add d to the y value, add negative 4 to negative 9, and that will become negative 13. Okay, so 1 comma negative 13. So really what this problem is saying, again, it's a little bit maybe difficult to decode what the question's asking of you. It's saying we have a function, and there's a specific point on that function. When we plugged in the 2, we found out that that point was really 2 comma 9. So really what they're saying is, what does 2 comma 9 become after all of the transformations in this problem? And that's what we just did, okay? So problem number 7 is exactly the same, with the exception of we now have a b value. So I wanted to remind you about the b value. B and c exist in the exponent for exponential functions. That's the inside of this function. So we need to put it in this form before we actually talk about a, b, c, d. So make sure that the coefficient of x is alone. Okay, so now I'm going to do the same thing. I'm going to start off with 2 comma 9. I'm going to go down instead of going across. Okay, so I'm going to start off with 2 comma 9. Okay, pick a different color. Okay, and we are going to, pick a different color. And now we are going to do the problems in order. So it says b first. My b value is 2, so I'm going to do a b transformation. Okay, and you got to be careful. B says take the reciprocal of b, multiply that by the x coordinate. So the reciprocal of 2 is a half. So it's really saying take half of my x coordinate. That would make that a 1. Right? So it's 1 comma 9. Okay? So now I have to do a c transformation, which is also on the x coordinate. Okay? So that says add 2 to the x coordinate, and it's my most recent x coordinate. So now this is going to become 3 comma 9. And again, that's my c. And now I'm going to do this again. I have a, A starts affecting the y coordinate by multiplying by -1, right? So remember, this is -1 times that base. So I'm going to say this is now 3 comma -9, okay? And now I have a D transformation, which says add the D value to y, add 7 to the y. That would make this 3 comma -2. So my final point, okay, it says use transformations to find the coordinates of the point on g of x. That point is this one right here, 3 comma -2, okay? So transformation showing up in our exponential unit. Okay. Problem number 8 and 9, find the value of m, which m shows up in both of the problems, okay, that makes the equation true. So what they're basically saying is, how can I transform the right-hand side so it's equivalent to the left-hand side? Because right now, 3 to the 3x plus 5 is definitely not the same as 27 to the x plus 1. So we're basically saying, what can I make m so that the left and the right-hand side will be the same? So the very first thing you want to do with these problems is try to get the bases to match, because when the bases match, the only thing we have to do is figure out how can I get the exponents to match as well. So I'm really going to look at the 27 and say, you know what, I'm going to make this 3 to the third times x plus 1. Okay, and I'll leave the right-hand side alone for the moment. I'm just really focusing on getting them to match. Okay, so I'm going to distribute this out. 3 to the 3x plus 1 equals m times 3 to the 3x plus 5, right? So now when I look at these, it's a little bit more obvious that they're pretty close to each other. If you notice that it's 3 to the 3x, this is also 3 to the 3x. So I don't need to change that at all. The only thing that I need to do is to change on the right-hand side. I need this 5 to turn into a 1. And so the question is, how do I turn 5 into a 1? Well, I would need to subtract 4. And so now we're kind of saying, well, how do I subtract 4 and change an exponent? So you got to go back to your exponent rule. So let me remind you about something. Like, let's say I had an exponent like, I don't know, 2 to the 7th power. And I would like this to become, I would like this to be equal to 2 to the, I don't know, to the 2nd power, okay? So really, what would I have to have here? If you go back to your properties of exponents, we have a property of exponent that says if you multiply, which that's really what we're doing in our problem, if we multiply together things that have the same base, add the exponents. So I want to add what to 7 to turn it into a 2? And the answer is I want to add a -5, right? So if I multiply this out, 2 to the 7th times 2 to the -5th, that is 2 to the 2nd. So if I want the value of 7 to decrease and become a 2, I need to multiply it by a negative exponent. So that's really what we need to do in our problem. I would like this 5 to turn into a 1, which means I need to multiply it by a negative exponent, in this case a -4. So that's what I'm going to do. I'm going to say the only thing that m could be is 3 to the -4th power. Okay? And so let's just check and see if this works. Okay? Which of course it's going to work, because I picked it to work specifically, but I want you to see it happen, okay? Really what this is saying is multiply these together, add the exponent. So -4 plus 5 is in fact 1, okay? So if it says find the value of m, 3 to the -4th, I'm just going to simplify that. That is 1 over 3 to the 4th. 1 over 3 to the 4th is really 1 over 81. So if I want the left and the right-hand side to be the same, I need the value of m to be 1 over 81 so that my exponent rules do what they should to turn this 5 into the one that's happening on the left. Okay, so again, a little bit tricky process there. You have to really work your way backwards, and you need to understand your properties of exponents to figure out how to turn that 5 into something that you want. So let's see this again, and hopefully it'll click maybe the second time if it didn't on the first one. So again, I'm going to make the left-hand side and the right-hand side have the same base so that I can just worry about their exponents. And it looks like the common base of 16 and 64 is a base of 4. Okay, so I'm going to leave the m alone. Okay, let's pick purple for this one, and we are going to say m times, and I'm going to turn 16 into a base of 4, which would be 4 squared. Okay, times 3x plus 2. Okay. And then the right-hand side is 4 to the 3rd, so it's 4 to the 3rd times 2x, okay? So let's simplify just these exponents and see where we're at. So this says now m times, the exponent's going to become 6x plus 4, 4 to the 6x plus 4, okay? And then on the right-hand side, this is just going to become 4 to the 6x, okay? So I kind of have the same situation here, where if you notice, again, these are actually pretty similar to each other. They're both 4 to the 6x. So the only difference between these is that on the right-hand side, I don't have that plus 4, which means what my goal is going to be is on the left-hand side, when I create m, I'm going to create it so that it cancels out this plus 4. And again, we just saw with the properties over here that really just means make it to 4 to the negative 4. Negative 4 plus 4 will cancel, okay? And now this is equivalent, okay? So I specifically picked that value because when I multiply together these bases, I'm going to add the exponents, and negative 4 plus 4 will go away. So my m value is 4 to the negative 4, which is really 1 over 4 to the 4th. 4 to the 4th power is 256. Okay, so I'm going to say in this case 1 over 256 is the m value that I need for this equation to be true. Okay, so let's do one more problem in this video, and then we will complete the rest of them in the next video. So problems 10 and 11, it says be sure to check for extraneous solutions. These are just solving problems. Okay, so in this case, this is very straightforward. I'm seeing very similar to the first group of problems that we did. I think it was problem 5 and 6, or 4 and 5. This is just a conversion. We're going to say 3 to the second power is equal to this expression. So x squared plus 10x plus 18 is equal to 3 squared. Right, 3 squared is 9, and I'm just going to take the step of subtracting that 9 over here just to save us a little bit of work. So it's 10x, and when I do 18 minus 9, I get a 9, okay? And that equals 0 now. I can factor and get x plus 1 and x plus 9, okay? And so I'm getting two solutions. X equals negative 1, x equals negative 9, and we need to make sure that these answers work. I'll let you plug them back into this log expression. They do, in fact, give you good answers for both of them. So these are negative x values, and they are actually good. We don't have to worry about any negative answers. So check them, but in this case, when we check them, we should be good to go. Okay? So problem number 11, okay, is different. Okay, so be careful. This is the log on the left, log on the right example. So this means just drop the logs off the problem. And again, I'm going to kind of reorganize. This middle's all messy. So I'm going to make this just look like 3x squared minus 18x plus 30 equals 2x minus 2. And this is really just solving a quadratic. So let's subtract and add over those values on the right. So it's set equal to 0. Okay, so let me fix my pen again. Okay, so I'm going to say this is really 3x squared minus 20x plus 32 equals 0. Okay, and to the best of my knowledge, let's see if I'm remembering this correctly, I believe the factors were x minus 4 and 3x plus 8. So let's make sure this works. This is negative 12, and that is positive 8. Oh, I'm sorry, this is supposed to be negative. I was close. So this is supposed to be minus 8. Okay, so let's fix that, and then try it again. So this is really minus sign. So if I check, I get negative 12 and negative 8, which is negative 20. So these are the correct factors. So I can set each of these equal to 0. X equals 4. X equals 8 over 3. Okay, and I'll let you go back and check to see if those are extraneous solutions. But I believe, let's just do a quick check. 16 over 3. Yeah, I believe both of these are good as well. You shouldn't have any extraneous solutions in this problem. Okay, so I'm going to stop the video. In part 2, we'll start on problem number 12. Okay, doing some word problems and some stuff with ln and e in natural law.